Welcome to the first module of this video series. In the first module, we are going to extend the linear regression framework into nonlinear problems. So here's our plan. We're first gonna do a review of linear regression. Then we're gonna move on to basis expansion, both in this video, and then we're gonna do spline. From there, I'm gonna introduce a kernel trick, and we're gonna revisit spline again using the kernels. Okay, so the first thing, let's do a quick recap of linear regression. We can start with a paired data xi and yi, with I goes from 1 to n. That means there are n data points. Let's say that xi lives in some d-dimensional space, and yi are real numbers. And suppose that our data set looks like this. The goal here is to find the best fitted line to capture the relationship between x and y. And just one thing to be mindful here is that I'm writing xi for d dimension, and that usually include the intercept. So if we just expand it, it's going to be xi1 to xi d minus 1, because the first number is the intercept. That means there are d minus 1 features when xi is a d-dimensional vector in linear regression. That's common notation we are using. And so how do we solve for this best fitted line in linear regression? Well, let's consider this problem geometrically, and I can say that the best line is obtained when it lies close to the points. That means the distance between each point, say this point is yi, to the line is the smallest. So its corresponding point here is xi transpose beta. Then we can write down the distance in this way as yi minus xi transpose beta. We can take the absolute value and then sum over all the data points. So that's the total distance. But usually we don't like to deal with absolute values because they are very difficult to differentiate. So what we usually do is that we just replace that with a square. So that makes differentiation way easier. Let's call this L of beta. That's the objective function we want to minimize. And then, so how do we solve for this? Is that we want beta hat to be the minimizer of L of beta. So that's our goal here. So what we can do is that first I'm going to rewrite everything in matrix notation, and because that's commonly used, and we should get used to that. And let me just rewrite everything with matrix notation, and then we solve this problem. So let me define y vector as y1 all the way to yn, and then we can define the x vector as by combining all the data points as well as x1 transpose, x2 transpose to xn transpose. So this is going to be a n by 1 vector. This is n by d vector. And then we are, the beta vector is going to be beta 0. That's the intercept, beta 1 to beta d minus 1. That will be the d minus 1 times 1 vector. So using this, we can actually rewrite our L of beta as um, can write L as beta as y minus x beta transpose y minus x beta. So that's the objective we want to minimize. To solve this is very straightforward. We just take the derivative equals to 0. So dL of beta d beta equals 0. We want to solve this equation. Let's do a quick change of variable, call this thing U transpose. This is U, and then that will be dL over d beta equals to du d beta times dL du. That gives us minus x transpose, and then 2 times y minus x beta. So you just expand this as 2 minus x transpose y plus 2 times x transpose x beta. And we solve this one equals to 0. Then we can just move these terms to the other side. And that will give us x transpose x beta equals to x transpose y. So we got the form for beta equals to x transpose x inverse x transpose y. So that's how we solve this equation. It's pretty straightforward. We finally got a very nice closed form solution for linear regression problem. And so even for nonlinear problems, this whole framework is going to come up a lot because many times we can just convert our problems from nonlinear to linear and then solve it with the exact procedure. Just one more thing here is that if we want to make predictions for data, let's say we have a new data points. Um, x n plus 1, then we can just predict its corresponding y as x n plus 1 beta hat. And what does this mean geometrically is that suppose that suppose this is a fitted line, and then we have a new data set. Those new data points comes in x n plus 1. We just find its corresponding values on the line here as our prediction for these data points when we are when we want to do predictions in machine learning. Okay, so now we can talk about basis expansion to see how we can use this to solve for nonlinear problems. Okay, so in basis expansion, let's just define a specific example first. Let's say that our xi and yi has a quadratic relationship. Epsilon I, this is, and fxi equals to beta 0 plus beta 1 xi plus beta 2 xi squared. So that's a quadratic function. If we just want to plot it, it's gonna be something like this. And the best fitted curve between x and y is gonna be quadratic. Right, it's going to be this curve, but let's say that the only thing we don't know for this problem is a coefficient. So we want to find beta 0, beta 1, beta 2. So that's a problem. And how can we solve that? Well, we can just use the same framework, and then to basically minimize the distance from each point yi to its corresponding one on the curve. That's given by beta 0 plus beta 1 xi plus beta 2 xi square. Okay, we can just do the same and then write down the objective function L of beta equals to sum of I equal to 1 to n, and then let's take the distance square, yi minus f of xi square. Okay, that's gonna be, I just expand the f, beta 0 plus beta 1 xi. So that is the objective function we get, and then we can actually write the matrix form for this as well. So things will be crystal clear once you see that. So let's also define y as a vector from y1 to yn, our n by 1 vector. And then here I'm going to define a matrix Z to be this way as 1, x1, x1 square, and then all the way to 1 xn xn square, and our beta gonna be beta 0, beta 1, beta 2. So this is an n by 3 matrix. This is a 3 by 1 vector. And what we can do here is that we can we can do this. Let's first do this. Let's do z times beta to see what we got, and that's gonna be we just do the matrix multiplication. That's gonna be beta 0 plus beta 1 x1 plus beta 2 x1 square, all the way to beta 0 plus beta 1 xn plus beta 2 xn square. And that is our f, right? It's the same as f1 to fxn. So this is nice. That means we can rewrite the objective function L of beta as y minus z beta transpose y minus z beta. That is the exact same objective as our linear regression. And we can just directly write out the solution of beta hat without doing the same thing. So beta hat directly, we can write it out as Z transpose Z inverse Z transpose Y. So this is what happens, right? We just solve these nonlinear problems with linear regression. And so how did that even happen? Because geometrically we see that x and y has nonlinear relationship, right? They clearly are their relationship are nonlinear. So what happens is that this matrix Z here is doing something amazing. And because we have expanded our feature space to include the x square term, so this is a basis expansion part. And because in normal regular linear regression, we don't have the square terms here. We're just using the first two columns as our feature space. So when we expand our feature space to include a quadratic term, that's how we convert the problem into a linear problem. And let me just draw a geometrical picture here. So before our expansion, our data looks like this, right? And let's say that this is x and y. So our best fitted curve is going to be quadratic. You know, if you want to do if you want to do a linear fitting on this, it's going to be terrible, right? You're going to end up with some curves like this. That's totally not going to work. But what happens after the expansion, right? That's really the question. So after the expansion, we're actually we need to plot this in a 3D space. And this is x, this is y, and here we also have the x square as part of the space. And what's happened is that now we all have now we'll have a 2D space, 2D plane in this expanded space where our curve gonna live, right? Our quadratic curve lives entirely in this space, and the data points it's gonna be it just be gonna be near this plane, right? It can vary in the y direction, so it won't perfectly lies on this plane, but it's gonna be nearby. But this whole problem is, you'll see this problem here become a linear problem that we can solve with linear regression. Okay, but actually this plot here is not the important part because like for most of our modern problems, we're easily dealing with really high dimensional data that we cannot visualize it anyway. And the same thing is that the intuition kind of holds is that when we have a nonlinear problem, we can apply some transformation or play around with the dimensions to convert it into a linear problem. So that's gonna comes up a lot throughout this entire series. And this basic expansion is the first one and the most straightforward one for this. And there are a few things I want to say about this. Is that so the first is that so fx. So we are dealing with we just did one particular example with quadratic functions of f, but fx can be any function. Can be any function. You can do sine of x and e to the x or something like that, or just e to the cosine x. Like basically any function you can expand it into the feature space and then solve it with linear regression. But that also brings out a limitation for this method, right? So the limitation is that we need to specify f before feeding the data. Okay, that means, but sometimes, or more commonly, we don't know the relationship between x and y. All we get is the data. What we want to do is to learn from the data, to see like what type of functions is the best. That means we don't know if it's quadratic, if it's cubic or anything, right? We want to make no assumptions about f. So that's where the span function comes to play, and we're gonna spend a lot of time talking about that. Um, to That can solve this limitation. And the second limitation here is that it doesn't scale very well with dimension. And scale poorly with dimension. And let me give you an example. So let's say that our feature space is 20. We live in 20-dimensional space. And if we just do a quadratic expansion, that means we need to take the full combination between xi and xj, right? We need a full combination of that that gives us 20 times 20 equals to 400 features. Okay, that's not good. But if you do something even more like cubic, and that's gonna be 20 is xi, xj, xk to the third, that's gonna be 8,000 features. So this method can just easily explode with the increase of dimensions and the increase of the terms we want to include, right? If we want to take the combination of many functions, so that's not ideal, and so that's really the problems with basis expansion. And for the next video, I'm going to start with the spline function to see how we can address the limitation one of this method.